thank you so much for coming. This is maximizing database performance with isolation levels. We're going to talk about transaction isolation in all of the SQL Server and Azure SQL DB and Managed Instance and everything else products and why they matter and how you can perhaps find bottlenecks or increase the performance of your applications by investigating and understanding transaction isolation. So very quickly about myself, my name is Bob Pusateri. I am been working with databases for over 15 years now, based out of Chicago, do a lot of work with the community, have been very happy to be a volunteer here at BITS for several years in the past, so this is great. Probably the best thing on this slide is my contact information, so if you have any questions that we can't address during the session, or if you're watching a video of this later and you want to reach out, feel free to catch me on Twitter or X, or send me an email, or you can also find my info on my blog there. As with all sessions, feedback is appreciated. All the speakers here are looking to perfect our craft and improve our presentations, and I'd appreciate any feedback you can offer. If you thought it was great, that's awesome. If you didn't think it was great, that's fine too, but if you could offer some criticism, constructively perhaps, in the forum, that'd be great. All right, so our agenda is pretty simple at a high level. We're going to be talking about the basics of concurrency in general, and then how it actually feeds into the isolation levels that are offered by the SQL Relational Engine. All the materials for this talk, all the slides and the demo scripts and the references and everything else are available either at that QR code or sqlbob.com/dirtyreads. I will have this available again at the end as well, so if you want to get it at the end, that's cool too. So we're going to go back to computer science class for a few minutes here, just talk about what is concurrency, right? Concurrency is the ability for an operation to be broken up into smaller parts or chunks that can then be worked on independently of each other, perhaps at the same time. The ability for multiple operations to access a modify or shared resource at the same time, and the more parts you can break it up to and work on at the same time, well, that means you have more concurrency, and this is all well and good until some kind of limiting factor appears. So there's a famous computer science problem that was proposed by a rather famous Dutch computer scientist, Dijkstra, and he taught this actually, it was like the early 1950s, but he proposed it. It was called the dining philosopher's problem. As you can see on the screen, we have 5 philosophers sitting around a table. Each has a bowl of, in this case, pasta in front of them, and there are also 5 forks. In order for a philosopher to eat, well, you need 2 forks. You can't just have one. But they can only pick up 1 fork at a time, and when they're finished, both forks have to be put back on the table. And if a philosopher isn't eating, a philosopher is thinking. Okay, now, what happens if everybody picks up 1 fork? Well, then no one can get a second fork, and you would have some kind of, effectively deadlock, right? So we might need some kind of rule, like a time limit. Maybe once you pick up 1 fork, you have to acquire another fork within a period of time, or you have to release the fork that you had already picked up. What if some philosopher never ever gets to eat at all? What if they never get their food? They starve, literally. The term is actually starvation in computer science scheduling terms. So we can very easily, of course, translate this to databases, right? Instead of the dining philosopher's problem, this can be the database problem there. We still have our table there sitting around, not a data table yet, but instead of philosophers, we now have end users. Instead of bowls of pasta, we have data tables or data in general. And instead of forks, we now have locks, right? So this is very easy to understand. We have the same problems with multiple users accessing a database at the same time. These are very real problems. Now, some of these problems we can describe by what are called concurrency conflicts, right? There are 3 that are defined by ANSI. They are known as preventable read phenomena. They are dirty reads, non-repeatable reads, and phantom reads. And we'll discuss exactly what those mean in the coming slides. There's also 2 other things we'll touch on very quickly. Those are lost updates and deadlocks. And it's important to note at the bottom of the slide that ANSI specifies which behaviors are allowed at different levels of concurrency and isolation, but not actually how to implement the solutions. So we'll talk about the Microsoft-specific solutions, again, that SQL Server and Azure SQL DB are using in their implementations. The first is dirty reads, right? And this is where we're reading data that is not yet committed. So this is quite possibly data that was changed by another process and is still in flight. It was not actually committed. You can end up, as a result of dirty reads, and we'll see this in a demo in just a minute, you can end up reading data multiple times or not at all, actually. Usually the reason for allowing dirty reads is because some people believe it's faster. The problem is you might be getting a less accurate result as well, so you kind of got to weigh those 2. Next are non-repeatable reads or inconsistent analysis. This is where you have multiple queries that are in the same transaction that end up getting different results. This is the result of a transaction from another process committing some changes between multiple reads that you're doing. The third is phantom reads, and this only affects queries with a predicate or a where clause. The idea is that the result set membership will change. So if you have multiple queries that use the same predicate in the same transaction, they can return differing results. There are, like I said, lost updates or an update conflict. This is where you have one user's update that overwrites another user's simultaneous update, and it has to be simultaneous, right? If I have an update that I do and then milliseconds later someone else does another update, that's not simultaneous. That's just a high transaction load application at that point. But if you have two simultaneous updates, it could possibly, if there's an update conflict, end up being that the first update never occurred or appears that way. And it's important to point out that the SQL engine will not permit this in any isolation level, so it's not really an issue. I just wanted to bring it up here for completeness. Then we also have deadlocks, right? This is where you have two or more tasks that end up blocking each other, and I'm sure we've all probably encountered a deadlock at some point if we've been working as a DBA for any amount of time. You have two or more processes, each has a lock on some resource but needs a lock on another resource to be able to continue, and no work is able to be done by anybody because of this. So SQL Server has a deadlock detection system where it can detect them, and it will choose a victim and roll it back in order to resolve it. The victim is usually going to be the one that is has made the least amount of progress, and hopefully by rolling it back, enough locks will be released that the others will be able to clear themselves. Now, there's a bunch of different ways to address these issues. The two big families here are pessimistic and optimistic concurrency. If we're being pessimistic, then we're expecting conflicts to occur, and we're going to use locks to try to prevent those conflicts. So this is where you get the classic idea of readers blocking writers and writers blocking readers. If you're using SQL Server before SQL 2005, pessimistic concurrency was your only option. I hope nobody here is still using SQL Server from before 2005. But in 2005, they released optimistic concurrency, and this is where we're being a bit more optimistic, and we're saying conflicts may still be possible, but we don't think they're that likely, so we're going to use less locking. I am not saying there is no locking. There is still some locking that goes on with optimistic concurrency, but the idea is we're going to use less locking, and we're going to use something called the version store to try to resolve that. And again, we'll see this when we get to the demos. So with that, we're done with the education part of this, and we're actually going to dive into isolation levels. But before I get there, do I have any questions? Nope, no questions online? Okay, cool. All right, plow right ahead. So as I mentioned, there's pessimistic and optimistic concurrency, and SQL Server has 6 different isolation levels that implement these. So there are 4 pessimistic levels and 2 optimistic levels. Now you'll notice I have read committed, I say default. This is because if you just install or spin up a SQL Server out of the box and don't change anything and create a database, that database will be in the read committed isolation level. That's what they give you out of the box. You can change it to be read committed snapshot instead, and then that will apply to everything in that database. The other levels you have to specify implicitly, or explicitly rather, to be able to make use of them. Now, if you're curious how to tell what isolation level you're in, if you're not sure, first of all, if you're not sure, it's probably going to be read committed, but if you really want to check, you can run a command called dbcc user options. It will give you a bunch of information about the current connection. So if you're using Azure Data Studio or SSMS, each window, each tab you open is a different connection. Each one could have a different isolation level if you altered it. But one of the ones that it will spit back there, as you can see at the bottom, is your current isolation level, if you don't know. If you need to change an isolation level, the syntax to do it can be set at either the connection or the query level. You cannot change it server-wide. And as I said, default is read committed. If you want to change it beyond that, you can use this syntax at transaction isolation level. This will apply the change to all the queries going forward for the current connection. If you open another connection, another tab, what you just did here will not apply. You'd have to do it in the other window as well. If you want to apply it at the query level, this is where you use hints, right? So probably the most common one you would see is with no lock, which means to use read uncommitted instead. You have to apply this on a per table basis. This is a table level hint. So if you're joining multiple tables together in the same query and you want to use with no lock, you would have to actually specify it every time you mention each table in the query if there's multiples. So in pessimistic concurrency, as I said, we're being pessimistic, we're assuming problems, and we're going to use locking to prevent them. This is, again, the classic model. So readers do not block readers, right? You can have multiple processes reading the same thing at the same time. They're not going to interfere with each other. That's all good. But everybody else blocks each other, right? Readers block writers, writers block readers, and writers, of course, block other writers. And once again, we're expecting problems. Now, very briefly, just to talk about locks and what this actually means with the blocking here. There are a whole lot of different lock modes in SQL Server. The lock engine is rather complex, and if you go to the documentation, you can pull up a nice, confusing matrix like this with all the different locks and whether or not they're compatible with each other. I'm going to try to simplify this a little bit, so I'm only going to talk about two of them today, really. Those are going to be S, or shared locks, and X, or exclusive locks. Again, there's a bunch of others. Some I'll mention in passing, but for everything else, we're just going to talk about shared or exclusive locks. Now, locks exist in a hierarchy in the SQL lock engine. So there's 4 levels. There's the database level, the table, the page, and the row level. And just to show, if we do a read operation, so let's say we're running just a simple select query from a table, there's going to be a shared lock at the database level, and this shared lock basically just means I have an open connection into this database. I'm doing something, don't drop this database while I'm doing it. You ever try to drop a database, you get an error that there's a user connected to the database? It's because of this shared lock. Now, because